A boundary exists in space from which nothing, not even light, can return. This is the event horizon, the universe's ultimate point of no return. Stephen Hawking once remarked that black holes are not as black as they are painted, hinting at the profound secrets hidden within. We are about to cross that threshold and explore the mind-bending reality inside a black hole. By the end of this journey, you will understand what physics suggests lies beyond this cosmic veil. We will confront the enigma of the singularity and question if information can ever truly be lost. How do you picture the final frontier of space and time? An astronaut drifts closer to the black hole, unaware of the invisible line she is about to cross. From our perspective, she slows, her image stretching and reddening before freezing entirely at the brink. But for her, there is no jolt, no physical barrier. She simply passes from a universe where return is possible into one where it is not. This intangible boundary is the event horizon, a gateway defined not by matter but by gravity's ultimate power. Its size is described by the Schwarzschild Radius, a concept born from Carl Schwarzschild's solution to Einstein's equations of general relativity. This radius marks the precise distance from the black hole's center, where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing can escape from within this sphere. It is a one-way membrane in spacetime. As physicist Kip Thorne describes it, once you cross all possible futures, every path you could take lead inexorably inward toward the central singularity. The mathematics behind this is both elegant and profound, calculated from the mass of the black hole itself. A black hole with the mass of our Sun would have an event horizon only about 3 kilometers in radius, packing all that weight into an unimaginably small point of no return. Imagine the finality of that moment. You could not send a single photon back as a farewell message. You are utterly and forever isolated from the rest of the cosmos, severed from every connection you have ever known. This understanding of the horizon as a fundamental limit, separating the observable from the forever hidden, sets the stage for the violent drama unfolding just outside its edge. Peeling back that outer skin of the event horizon reveals a structure of astonishing complexity. A black hole is much like a cosmic onion, with layers of profound mystery hidden within. Just inside the event horizon lies a region called the Ergosphere, a wild and warped zone of spacetime. In a rotating black hole described by the Kerr metric, the Ergosphere is not static. It is dragged around by the black hole's immense spin, a phenomenon known as frame dragging where space itself is forced to move. An object caught here could theoretically extract some of the black hole's rotational energy before being pulled inward, a fleeting chance in a desperate situation. But the ultimate mystery lies at the very heart of this cosmic entity, the Central Singularity. This is a point of infinite density, where all the matter that ever crossed the event horizon is crushed into a volume of zero size. Here, the known laws of physics simply break down. The equations of general relativity that so elegantly describe gravity outside the horizon lead to infinities at this core, a clear sign that our understanding is incomplete. The renowned physicist Roger Penrose proved with his singularity theorems that, within the framework of general relativity, the formation of such a point is inevitable once a black hole forms. It is not a matter of if, but when. Consider a massive star collapsing under its own weight at the end of its life. All that immense mass, once spread across millions of kilometers, is compressed into an infinitesimal point. What does this tell us about the ultimate limits of gravitational collapse? It forces us to confront the fact that our concepts of space and time have a final frontier, a boundary beyond which they cease to have any meaning. This relentless inward pull, this journey toward an unknowable center, sets the stage for the next great mystery. What would it actually be like to travel through these layers and experience the titanic forces at play? That violent stretching into a cosmic noodle is not just a metaphor, it is a real physical process called spaghettification. The cause is a difference in force, a tidal effect, but on a scale far beyond any ocean tide. If you were to fall feet first toward a stellar mass black hole, the gravitational pull on your feet would be significantly stronger than the pull on your head. You would be stretched lengthwise, pulled apart like soft taffy, while simultaneously being compressed from the sides. This extreme deformation happens because the event horizon of a smaller black hole is so close to its central point of immense mass, creating an incredibly steep gravity gradient. The change in force over just the height of your body would be catastrophic. This is why stellar mass black holes are the most efficient noodle makers in the cosmos. For larger, supermassive black holes, the event horizon is so far from the center that the tidal forces at the boundary are much gentler. You might cross the point of no return without even noticing the difference, at least for a little while. But for any object encountering a smaller black hole, the effect is swift and brutal. An asteroid, a planet, or even a star that drifts too close can be completely torn asunder. The star's own gravity can no longer hold it together against the black hole's relentless pull. It is shredded into a long, thin stream of incandescent gas, a process that releases a brilliant flash of radiation as the material is heated to extreme temperatures. This is how astronomers often detect these dark predators, by the death cries of the stars they consume. So what would it be like to experience this firsthand? Your body would be subjected to forces beyond comprehension, stretched into a stream of atoms long before you reach the central mystery. This violent transformation at the doorstep is merely the beginning, a physical prelude to the profound breakdown of reality itself that waits within. That image of an astronaut frozen forever at the brink is not an illusion, but a direct consequence of time itself warping under extreme gravity. Picture a clock falling toward the event horizon. From your safe vantage point far away, you would see its hands slow down, ticking with agonizing lethargy until they finally, completely stop. The clock and the astronaut holding it would appear to hang there for all eternity, their image stretched and reddened into nothingness. This is gravitational time dilation, a real effect predicted by Einstein's theory of general relativity. Time does not pass at a single universal rate. It flows more slowly where gravity is stronger. The mathematics reveals a staggering truth. At the precise boundary of the event horizon, the equations tell us that time dilation becomes infinite. To an outside observer, nothing ever actually crosses the horizon. It just approaches it more and more slowly, fading from view over what would be billions of years. This creates a profound paradox. For the astronaut falling in, her watch continues to tick normally. She feels no sudden stop. She crosses the point of no return in a finite amount of her own time, completely unaware that from your perspective, her journey inward has effectively been paused forever. Physicists like Brian Greene have grappled with this strange duality where two realities seem to coexist, one for the observer and one for the falling object. This turns a black hole into a kind of cosmic time capsule, preserving the final moments of anything that ever fell in, a fossilized image etched onto the surface of the horizon for all time. Imagine a space probe on a one-way mission, programmed to send back data as it descends. Each signal would take longer and longer to arrive, the waves stretched to lower and lower energies until they were too faint and too slow to ever be detected. The last message from the probe would never truly reach us, its final farewell lost to the stretching of time itself. What does this say about the nature of reality? It suggests that what we can observe is not the entire story, that our perception is limited by the very laws of physics. This incredible distortion of time, a purely relativistic effect, is our first major clue that the event horizon is not just a physical boundary, but a quantum one as well, where the fabric of spacetime reveals its deepest secrets. This paradox strikes at the very heart of physics. Toss a book into a black hole, and from a classical view it is gone forever, its words and pages lost behind the event horizon. Yet quantum mechanics, the rulebook for the subatomic world, states with absolute certainty that information can never be truly destroyed. It might be scrambled beyond recognition, but it must, in principle, be recoverable. This is the information paradox, a profound conflict between our two most successful descriptions of reality. The crisis was ignited by Stephen Hawking. He calculated that black holes are not perfectly black. They slowly leak a faint glow of particles, now known as Hawking radiation. This radiation, he argued, is entirely random, carrying no information about what fell in. As the black hole emits this radiation, it loses mass and eventually evaporates, vanishing completely. If that happens, the information locked inside vanishes with it, violating a foundational pillar of quantum theory. Hawking had seemingly proven that information could be erased from the universe, an idea so troubling he famously bet against it, only to later change his mind. His reconsideration opened the door to even stranger possibilities. If information is not lost, then how does it get out? One compelling answer comes from the holographic principle, championed by physicists like Leonard Susskind. This radical idea suggests that all the information about everything that falls into a black hole is not lost inside, but is instead perfectly encoded on the two-dimensional surface of its event horizon, like a cosmic DVD. The three-dimensional interior we imagine is just a projection of this data stored on its boundary. This leads to the dizzying concept of black hole complementarity, which proposes that there are two equally valid stories of what happens. From the outside perspective, information never crosses the horizon. It is smeared and stored on the surface, eventually leaking out with the Hawking radiation. But from the perspective of someone falling in, they simply pass through the horizon uninterrupted, seeing no data on the wall. Both stories are true in their own reference frames, a bizarre but necessary reconciliation. This delicate compromise, however, was threatened by the Firewall Paradox. If information is being dutifully encoded on the horizon to be released later, the calculations suggested that the horizon should not be the smooth region of space we thought. Instead, it might be a seething, energetic wall, a literal firewall that would instantly incinerate any astronaut crossing the boundary. Now we face a trilemma. Three things we thought were true cannot all be correct. Either information is lost, which breaks quantum mechanics. The horizon is a deadly firewall, which breaks general relativity, or our most basic assumptions about locality and reality are wrong. This is not just a philosophical debate. It forces us to invent new physics, pushing string theory and loop quantum gravity to their limits in search of answers. What is the ultimate fate of knowledge in the cosmos? The resolution will likely reveal that spacetime itself is not fundamental, but emerges from something deeper, something woven from quantum information. Empty space is never truly empty. It is a seething quantum foam where pairs of virtual particles constantly flicker into existence, borrowing energy from the vacuum only to annihilate each other and vanish an instant later. This strange quantum dance holds the key to a black hole's slow demise. When this process happens right at the precipice of the event horizon, the delicate balance is shattered. One particle of the pair can be captured by the black hole's gravity, plunging across the point of no return while its partner is left stranded, free to escape into the cosmos. To conserve energy, the particle that escapes must have positive energy, and the one that falls in must have negative energy relative to the outside universe. The black hole essentially pays for the escaped particle's existence by losing a tiny fraction of its own mass. This slow, relentless leak is Hawking radiation. It is not a fiery jet of material exploding from the black hole, but a faint, cold glow of particles slowly bleeding its mass away into the void. The process is rooted in quantum field theory, applied to the warped spacetime around a black hole, where the event horizon acts as a one-way filter for these quantum fluctuations. For a black hole with the mass of our Sun, this radiation is so faint, so whisper-quiet, that it is utterly drowned out by the cosmic microwave background. The black hole would absorb more energy from the universe's leftover heat than it emits, causing it to grow, not shrink. But for a much smaller black hole, the story is different. The evaporation rate accelerates dramatically as the black hole loses mass. A black hole with the mass of a small asteroid would glow with the heat of a million-degree furnace, shedding its mass in a final, explosive burst. This leads to a startling possibility. The early universe, dense and turbulent, might have created vast numbers of these tiny primordial black holes. Some could be evaporating right now, their final moments marked by a brilliant flash of gamma rays that we could potentially detect. How does this change our view of black holes as eternal prisons? They are transformed from permanent graves into dynamic, evolving objects with a finite lifespan. Yet this very escape mechanism deepens the information paradox. As physicist Carlo Rovelli explains, Hawking radiation is thermal, it is random heat. It carries no fingerprint, no hidden code about the book, the star, or the astronaut that fell in. If the black hole evaporates completely, leaving behind only this featureless radiation, where did all that intricate information go? The universe's most secure vault does not just dissolve, it seemingly burns its contents to ash, leaving no record behind. At the heart of this cosmic collapse, the journey inward reaches its final, incomprehensible destination. Deep within the black hole, shielded from our view by the event horizon, lies the singularity. This is not a place you could ever see or touch. It is a point of infinite density where all the mass that ever fell in is crushed into a volume of zero size. According to the equations of general relativity, the curvature of spacetime here becomes infinite. The very fabric of the universe, the stage upon which all events play out, is torn apart. Our most trusted laws of physics simply cease to function, their equations dissolving into meaningless infinities. This is not a failure of mathematics, but a signpost that we have reached the ultimate limit of our current understanding. Roger Penrose's profound theorems show us that the formation of such a singularity is not a rare fluke. It is an unavoidable and generic outcome of a complete gravitational collapse. Once a certain point is passed, the formation of a black hole and its central singularity becomes inevitable. The nature of this endpoint depends on the black hole itself. For a simple, non-rotating black hole, the singularity is thought to be a single, terrifying point. But the universe is rarely so simple. Most black holes are thought to spin, and for these dynamic objects described by the Kerr solution, the singularity might take on a different form. It could be a ring singularity, a loop of infinite density that, in theory, you might even pass through. The implications of this are staggering, potentially opening pathways to other regions of spacetime, though such journeys remain purely speculative. This bizarre landscape is where our greatest theoretical challenge is born. The infinite predictions of general relativity at the singularity scream for a deeper theory, one that can marry the vast scale of gravity with the fuzzy rules of the quantum world. Quantum gravity theories like loop quantum gravity propose a radical solution. They suggest that the intense pull of gravity is ultimately counteracted by a powerful quantum repulsion. Instead of a true point of infinite density, matter might be crushed into a tiny but finite super-dense state and then rebound in a cosmic bounce. Imagine the very core of a collapsed star not as a dead end but as a transition, a gateway to something entirely new. What then truly lies at this ultimate endpoint? The singularity is not an answer but a question mark written into the fabric of reality itself, forcing us to invent new physics to read what comes next. This elegant simplicity is known as the No-Hair Theorem. A black hole, for all its terrifying power, can be completely described by just three numbers: its mass, its electric charge, and its spin. Everything else, every intricate detail about the stars, planets, or astronauts that fell in, is permanently erased. It does not matter if the black hole formed from a sphere of perfect iron or a chaotic cloud of 1,000 different elements. Once the event horizon seals shut, the only remaining properties are these three bare quantities. Physicist John Wheeler, who popularized this idea, captured its essence perfectly. Black holes have no hair. They are bald, featureless objects in the cosmic landscape. This profound simplicity is a gift for theorists. It means the incredibly complex mathematics of general relativity becomes manageable, allowing us to describe the entire spacetime around a black hole with stunning precision using solutions like the Kerr metric for a spinning hole. The great astrophysicist Subrahmanyan Chandrasekhar marveled at this mathematical beauty, seeing it as a deep triumph for Einstein's theory. Yet this very elegance creates a terrible conflict. Quantum mechanics insists that information about what fell into the black hole cannot be truly destroyed. The No-Hair Theorem seems to say it is wiped clean, leaving us with the original information paradox in its starkest form. How can a black hole be so simple if it is supposed to remember everything it ever consumed? This contradiction has forced physicists to ask if black holes are truly as bald as they seem. Could there be hidden features, what some call quantum hair, that subtly record information without violating the classical rules? In some extensions of general relativity, involving new types of fields, or in the complex frameworks of string theory, this quantum hair might exist. It would not be a physical puff of fuzz, but an imprint, a subtle encoding of the fallen matter's history in the structure of spacetime itself right at the horizon. This suggests that the perfect simplicity of the No-Hair Theorem might be an illusion, a beautiful approximation that breaks down when quantum gravity enters the picture. The search for this quantum hair is really a search for the missing link between the smooth geometry of general relativity and the frantic, information-preserving world of the quantum. Are black holes the universe's ultimate erasers, or are they the most complex libraries imaginable, with every book written in a language we have yet to decipher? Could the crushing singularity at a black hole's heart be a bridge instead of an end? One of the most tantalizing possibilities hidden within Einstein's equations is the Einstein-Rosen bridge, a theoretical tunnel connecting two separate points in spacetime. Picture a vast cosmic wormhole, a shortcut that could, in theory, link distant galaxies or even different universes. This is not mere science fiction. It is a legitimate, though highly unstable, solution to the same mathematics that predicts black holes. The classic model, explored by physicists like Nathan Rosen, connects the interior of a black hole to a hypothetical white hole. A white hole would be the exact opposite of its dark counterpart, a region of spacetime from which matter and energy can only emerge, never enter. It would be a fountain of cosmic rebirth, violently expelling everything that ever fell into the linked black hole. Yet this elegant symmetry hits a brutal wall with reality. White holes are thought to be fantastically unstable if they could form at all. The second law of thermodynamics, which dictates that disorder always increases, seems to forbid their existence. A white hole would essentially be a machine that decreases entropy, a cosmic violation that nature appears to prohibit. For the wormhole itself, the problem is even more immediate. The gravitational forces within the tunnel would be so immense that the bridge would snap shut in an instant, crushing anything attempting to pass through. The journey would be shorter than a blink of an eye and just as fatal. So how could such a passage ever be used? This is where the realm of speculation pushes physics to its limits. To prop the wormhole open, you would need a form of exotic matter. This is not antimatter, but something far stranger, a substance with negative energy density that would effectively generate negative gravity, pushing the walls of the tunnel apart against their own immense weight. While such exotic matter is theoretically permitted in quantum field theory, we have never observed it in the quantities needed to stabilize a cosmic shortcut. The work of experts like Kip Thorne has shown that while traversable wormholes are mathematically possible, they demand physical conditions that border on the miraculous. Imagine a civilization with God-like control over spacetime, weaving threads of exotic matter to build a stable highway between stars. This idea fuels countless stories of interstellar travel and even time machines, as a wormhole could also connect two different moments in time. But what if nature builds these bridges herself without any need for engineering? Some interpretations of the complex interiors of spinning black holes suggest that the ring singularity might not be a wall but a portal. Falling through it could, in some mathematical models, transport you to another part of our universe or into a completely different cosmos altogether. In this breathtaking scenario, a black hole is not a grave but a one-way gate in an infinite multiverse. Your journey through the violent tides and warped space would culminate in a rebirth in a realm with entirely different physical laws. Is our entire universe, then, the white hole eruption from a black hole in another reality? These questions linger at the very edge of theoretical physics, where mathematics and imagination collide. They transform the black hole from a symbol of finality into a question about cosmic connectivity, challenging us to rethink the very nature of existence. The universe's most secure vault does not destroy its contents. It simply stores them in the most unexpected place. The event horizon itself becomes a cosmic hard drive, a two-dimensional surface that encodes a perfect description of the three-dimensional interior. This is the holographic principle, a revolutionary idea championed by physicists like Gerard T. Hooft and Leonard Susskind. Think of a common security hologram on a credit card. That flat, shimmering surface contains all the information needed to project a three-dimensional image. The holographic principle suggests that a black hole, and perhaps our entire universe, operates in a similar way. All the information about every star, every atom, and every astronaut that fell into the black hole is not lost in the Central Singularity. Instead, it is meticulously painted onto the event horizon's surface, translated into a language of incredibly tiny Planck-scale pixels. The evidence for this comes from black hole thermodynamics. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, which is a measure of its hidden information, is directly proportional to the area of its event horizon, not to the volume of its interior. This was a profound clue. In everyday life, the entropy of a room full of gas depends on its three-dimensional volume. But for a black hole, the maximum amount of information it can contain is limited by the two-dimensional area of its boundary. It is as if the interior has no independent existence. It is just a projection, a shadow cast by the data written on the spherical shell of the horizon. This radical notion finds a concrete mathematical foundation in the work of string theorists like Juan Maldacena. His discovery of the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT, provides a precise duality. In this model, a universe with gravity in its interior is completely equivalent to a quantum field theory without gravity living on its boundary. It is a perfect dictionary translating between two completely different descriptions of reality. This principle offers a stunning resolution to the information paradox. Information is never truly lost inside a black hole because it never actually falls in from a certain point of view. It is copied and stored on the horizon, and then slowly radiated back out into the universe as the black hole evaporates via Hawking radiation, scrambled but preserved. The implications ripple out far beyond black holes, challenging our most basic assumptions about reality. If the contents of a three-dimensional volume are encoded on its two-dimensional boundary, then our own vivid, three-dimensional world, with its mountains, oceans, and stars, might itself be a holographic illusion. The true workings of the cosmos could be written on a distant, two-dimensional surface, a fundamental screen at the edge of space. How solid, then, is the world you feel around you? The holographic principle boldly bridges the worlds of gravity and quantum mechanics, suggesting that space itself is not a fundamental stage, but an emergent property, a hologram generated by a deeper, information-based reality. Deep inside the black hole, where the pull of gravity becomes truly infinite, our current maps of reality dissolve into chaos. This is the domain where Einstein's elegant spacetime curves into a meaningless singularity, a clear signal that we need a new kind of physics. To understand what truly lies beyond the event horizon, we must find a theory that can unite the vast cosmic scale of general relativity with the frantic, probabilistic rules of the quantum world. This ultimate unification is the quest for quantum gravity, a framework that would describe the violent quantum foam churning at the heart of a black hole. Two leading approaches offer radically different pictures of this hidden realm. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrations of these strings give rise to all the forces and particles we see, including the fabric of spacetime itself. In this view, the apparent singularity might be smoothed out by these underlying vibrations, preventing true infinity. The other major path, loop quantum gravity, takes a more direct approach. It suggests that space itself is not smooth and continuous, but is woven from a fabric of finite, incredibly tiny loops. Picture the universe as a tapestry made of individual threads with a smallest possible stitch. At the Planck scale, a distance a billion trillion times smaller than an atom, space-time becomes granular. This has a profound implication for the black hole's core. Instead of matter collapsing into an infinitely dense point, the intense gravitational pull would eventually be met by an equally powerful quantum repulsion. Physicist Lee Smolin and others have explored this idea, suggesting the singularity is replaced by a quantum bounce. Imagine the collapse of a star not as a final crunch, but as a cosmic rebound. The matter squeezed beyond comprehension would spring back, potentially transforming the black hole into something else entirely. This could be a gateway to another universe, or even a transition into a white hole, violently spewing the collapsed material back out. The challenges in merging these two worlds are immense. How do you reconcile the smooth, geometric landscape of general relativity with the discrete, jittery nature of quantum mechanics? The answers may eventually come from observations. As two black holes spiral together and merge, the resulting gravitational waves ripple through space-time. Some quantum gravity models predict that the event horizon might not be a perfectly smooth membrane, and this imperfection could leave a faint imprint on those waves, a tiny echo of the quantum structure within. What new physics awaits in this realm where space and time are born from something deeper? The quest to bridge this divide is not just about saving the equations, it is about uncovering the true nature of reality at its most extreme. A black hole is a thermodynamic engine governed by laws as precise as those controlling a steam engine. This remarkable connection was forged by the work of Jacob Bekenstein and Stephen Hawking, who realized that a black hole is not a cold, dead thing. It possesses both entropy and a temperature, a faint heat born from the quantum whispers at its event horizon. The entropy, which measures the hidden information within, is not proportional to the black hole's volume, but to the surface area of its horizon. This was Bekenstein's great insight, a clue that the true nature of reality might be written on a surface, not contained in a volume. Hawking then showed that this temperature is manifested as the very radiation that bears his name, the slow leak that causes a black hole to eventually evaporate. From this foundation, 4 laws of black hole mechanics emerged, mirroring the classic laws of thermodynamics with uncanny precision. The zeroth law states that the surface gravity across a stationary black hole's event horizon is constant, much like the uniform temperature of an object in thermal equilibrium. This surface gravity is directly related to the black hole's temperature. The first law is a kind of energy accounting, relating the change in a black hole's mass to changes in its horizon area, its spin, and its electric charge. It is a conservation equation for the cosmos's ultimate sink. The second law, famously championed by Hawking, dictates that the total area of all event horizons, and thus the total entropy of all black holes, can never decrease over time. This aligns perfectly with the universal tendency toward disorder. Finally, the third law suggests that it is impossible to reduce the surface gravity of a black hole to absolute zero through any physical process, meaning a so-called extremal black hole represents an unreachable state. The entropy of a typical black hole is staggering. For one with the mass of our Sun, the entropy would be a number with about 78 digits, vastly greater than the entropy of all the star's original particles scattered across space. This colossal number hints at an almost unimaginable number of microscopic configurations, or microstates, hidden within. What are these microstates? According to the Holographic Principle, they are the quantum gravitational degrees of freedom, the fundamental bits of information that are encoded on the event horizon's 2-dimensional surface. This thermodynamic view elevates black holes from cosmic anomalies to fundamental actors in the universe's grand play. They are not exceptions to the rules, but their ultimate expression, revealing a deep and hidden order where gravity, thermodynamics, and quantum mechanics converge. If a black hole has entropy and temperature, it must have a structure, a quantum mechanical architecture we are only beginning to fathom. This peaceful passage through the event horizon might be a fantasy. Quantum mechanics could demand a far more violent welcome. The Firewall Paradox presents a terrifying scenario where an astronaut crossing the boundary is not met by empty space, but instantly vaporized by a searing wall of high-energy particles. Proposed by physicists Almary, Marolf, Polchinski, and Sully, this puzzle arises from a brutal tug of war between 3 cherished principles. We have Einstein's equivalence principle, which assures us that free fall should be smooth and unremarkable. Then we have quantum mechanics, which insists that information can never be destroyed. And finally, we have the assumption that physics works the same everywhere. The firewall argument shows that you cannot have all 3 at the event horizon. To preserve information as quantum law requires, the horizon cannot be the quiet place general relativity describes. Instead, it must be a site of immense energy, a literal firewall that burns anything to ash. The late Joseph Polchinski and his colleagues argued this was a necessary, if shocking, consequence of saving information from being lost forever. This would resolve the information paradox, but at a terrible cost, forcing us to abandon Einstein's bedrock principle that a person in free fall feels no special forces. The universe seems to be presenting us with an impossible choice. Either information vanishes, breaking quantum theory, or the event horizon is a deadly inferno, breaking general relativity. This dilemma has spurred radical alternatives. One compelling idea from string theory is the Fuzzball Proposal. In this view, the black hole's interior does not exist at all. Instead of an empty space leading to a singularity, the entire region inside the event horizon is filled with a tangled, quantum gravitational ball of strings, a fuzzy structure that has no sharp boundary. An astronaut would not pass through a horizon and get burned. She would simply collide with this complex, impenetrable object. There is no smooth spacetime to traverse, and therefore no paradox about what happens when you cross a line that is not really there. Does physics truly demand a firewall, or is nature more clever, finding a way to preserve information without violating the smooth fall of spacetime? This paradox is not a flaw in our theories, but a gateway, forcing us to confront the very nature of reality at its most extreme. That smooth, empty space inside the event horizon might be a grand illusion. String theory offers a radical alternative, where a black hole is not an empty pit but a tangled, vibrant object called a fuzzball. Proposed by physicist Samir Mathur, this idea suggests the entire region we think of as the black hole's interior is filled with a complex, fuzzy ball of fundamental strings and their higher dimensional cousins, brains. There is no sharp event horizon and no central singularity. The surface of this fuzzball is the effective boundary, a quantum mechanical structure without a point of no return in the classical sense. This profound shift in perspective resolves the information paradox with elegant simplicity. Since the fuzzball is a specific, complicated quantum state, the information about everything that formed it is not lost behind a horizon. It is woven directly into the intricate structure of the fuzzball itself, like a cosmic tapestry recording its own history. When the fuzzball emits Hawking radiation, that radiation is not random thermal noise. It carries the specific imprints of the information stored within, ensuring nothing is ever truly erased from the universe. This proposal also elegantly sidesteps the terrifying firewall paradox. If there is no sharp, classical event horizon, then there is no specific line where the laws of physics break down and a wall of fire must appear. An astronaut approaching a fuzzball would not experience a smooth passage followed by incineration. Instead, she would simply collide with the fuzzball's surface, a complex quantum object, and her information would be absorbed and stored within it. The work of experts like Andrew Strominger on microstate geometries supports this general picture, showing that what we perceive as a single black hole could actually be a superposition of countless different, specific quantum configurations. Each fuzzball is one of these microstates. Calculations reveal that a collection of fuzzballs can perfectly reproduce the famous thermodynamics of black holes, matching their entropy and temperature without any need for a mysterious, information-destroying singularity. This transforms our view of black holes from simple, bald pits governed by three numbers into the most intricate and complex objects in the cosmos. They are not featureless graves but dynamic quantum systems. What if the universe's most powerful gravitational phenomena are ultimately quantum objects in disguise? The Fuzzball Proposal is a bold step toward unifying the worlds of gravity and quantum mechanics, suggesting that spacetime itself emerges from a deeper, vibrating reality of strings. The invisible architecture of the cosmos directly shapes the life cycle of a black hole. Our universe is filled with dark matter, a mysterious substance that gravitates but emits no light, and dark energy, a repulsive force accelerating cosmic expansion. These unseen players orchestrate the growth and ultimate fate of these gravitational giants. Picture a supermassive black hole at the center of a galaxy, like our own Milky Way. It sits within a vast, invisible halo of dark matter, a ghostly gravitational well. As stars and gas clouds swirl around it, the black hole also pulls in this dark matter. While dark matter particles rarely collide with each other, their collective gravity creates a dense, shadowy reservoir that constantly feeds the black hole's mass, influencing its growth over billions of years. The pioneering work of astronomers like Vera Rubin, who revealed the flat rotation curves of galaxies, provided the first compelling evidence for this dark gravitational glue. Her observations showed that stars at the edges of galaxies move far too quickly to be held in place by the gravity of visible matter alone, pointing to the pervasive presence of dark matter. This same gravitational influence can funnel dark matter toward the central black hole, acting as a steady, invisible fuel source. Some theories even suggest that dark matter particles could annihilate upon contact near the event horizon, releasing bursts of energy that further influence the black hole's environment. Could the very first black holes have been forged from the dense fluctuations in the dark matter-rich early universe? Many scientists think so, proposing that some primordial black holes are themselves the elusive dark matter, ancient relics from the cosmos's first moments. Yet, as black holes feed, the universe itself is stretching apart at an ever-increasing rate due to dark energy. This cosmic acceleration presents a paradoxical future. In a universe dominated by dark energy, often modeled as a de Sitter space, the fabric of spacetime is being pulled taut. This expansion could, in theory, affect the Hawking radiation process, potentially causing isolated black holes to evaporate faster as the universe cools and stretches into emptiness. The long-term duel between a black hole's gravitational pull and the universe's inflationary push will dictate its final moments. We are now testing these profound ideas by listening to the echoes of black hole collisions. When two black holes spiral together and merge, they ripple the fabric of spacetime, sending out gravitational waves that we can detect here on Earth. The characteristics of these waves carry information about the black hole's masses and the environment they formed in, potentially revealing the fingerprints of a dark matter halo. How does the presence of a dense cloak of dark matter alter the dance of a binary black hole pair? Each merger we observe is not just a cataclysm, it is a cosmic experiment, probing the invisible forces that govern the universe from within the deepest shadows. Could a black hole be a one-way ticket to another reality entirely? The mathematics of general relativity does not forbid it. When we trace the path of an object falling into a black hole, the equations do not necessarily end at the singularity. They can continue, describing a bridge to another region of spacetime. This is the Einstein-Rosen bridge, a wormhole that could theoretically connect our universe to a different one. The journey would not be a gentle one. You would be navigating the most violent terrain in the cosmos, stretched by tides, and navigating the warped geometry near a ring singularity. But if you survived, the equations suggest you might not find yourself in the heart of a crushing gravity well, but spewed out into a new cosmos from a white hole, a region of spacetime that only expels matter and energy. This is not a stable subway system for interstellar travel. The tunnel would likely collapse instantly, crushed by its own gravity. To hold it open would require exotic matter with negative energy, a substance we have never seen in the necessary quantities. Yet, this speculative doorway forces us to confront an even grander possibility, the multiverse. What if our universe is not alone? The theory of eternal inflation suggests that the rapid expansion of the Big Bang is still happening in a vast background space, constantly spawning new bubble universes with different physical laws. In this cosmic landscape, a black hole could be a rare puncture in the fabric of our bubble, a place where the space-time of two distinct universes briefly touch. Some interpretations of quantum mechanics go even further. They propose that the singularity at the heart of a black hole is not a dead end, but a bounce. The intense quantum gravitational pressure could be so immense that it triggers a new Big Bang, creating an entire infant universe in a hidden dimension, with its own space-time, its own stars, and its own laws of physics. In this breathtaking scenario, our own cosmos might have been born this way. The philosopher of science Max Tegmark categorizes multiverses into different levels, from regions of space too distant for us to ever see, to universes with entirely different fundamental constants. A black hole could be a gateway to any of them. This leads to a profound thought. What if every black hole is a seed for a new reality? Every time a star collapses into a black hole, it might not be creating a tomb, but a cosmic womb, giving birth to an entire universe within its hidden depths. The matter that falls in does not vanish into nothingness. It becomes the raw material for a new cosmos with its own history and future. This idea, known as black hole cosmology, suggests that our entire expanding universe could be the interior of a black hole existing in a larger parent universe. The event horizon we ponder from the outside would then be the Big Bang from the inside, the ultimate beginning. This transforms the meaning of beyond the event horizon from a question of physics into a question of existence itself. Are we living in someone else's black hole? We cannot see past the event horizon, but its shadow is unmistakable. The brilliant ring of light surrounding the dark void in the event horizon telescope's image of the black hole in galaxy M87 is a perfect example. That central darkness is not the black hole itself, but its shadow, a silhouette cast against the glowing matter swirling around it. The sharp boundary of that shadow corresponds directly to the event horizon, giving us our first direct visual evidence of this cosmic point of no return. Long before this iconic image, astronomers relied on other ingenious methods to study these invisible objects. In X-ray binary systems, a black hole and a normal star orbit each other. Gas ripped from the star spirals inward, forming a superheated accretion disk that emits intense X-rays just before the material vanishes forever across the horizon. The precise timing of these X-ray flickers reveals the extreme environment just outside the brink. Similarly, the colossal jets of plasma shooting from the cores of galaxies, visible across the universe, are powered by the immense rotational energy of the central supermassive black hole. These jets are a direct product of the warped spacetime and magnetic fields in the Ergosphere, the region just outside the event horizon we discussed earlier. We can even use gravity itself as a lens. When a black hole passes in front of a distant star, its gravity bends the starlight, causing the star to temporarily brighten, a phenomenon called gravitational microlensing that betrays the black hole's presence. Some of the most compelling evidence comes from patiently watching the motions of stars. For decades, astronomers like Andrea Ghez and Reinhard Genzel have tracked individual stars orbiting the invisible, massive object at the very center of our Milky Way, known as Sagittarius, a star. By meticulously mapping these frantic orbits, they calculated an astonishing mass. Something equivalent to 4 million suns is crammed into a region smaller than our solar system. The only object that can possibly contain so much mass in such a small volume is a supermassive black hole, a discovery that earned them a Nobel Prize. Then there are the ripples in space-time. When two black holes spiral together and merge, they shake the very fabric of the cosmos, sending out gravitational waves. Observatories like LIGO and Virgo have detected these echoes from multiple collisions, each signal providing a wealth of information about the black hole's masses and spins before they merged. This data is a direct probe of the dynamics just outside their event horizons. Supercomputer simulations bring all these clues together, modeling how hot plasma swirls into the abyss, how magnetic fields are twisted into powerful jets, and what the flickering light from quasars tells us about processes happening near the ultimate edge. The future promises even sharper vision. The space-based Gravitational Wave Observatory (LISO) will detect the mergers of smaller black holes across vast cosmic distances, while next-generation telescopes will watch stars dance with ever greater precision. So what can these observations tell us about the forbidding interior? They provide the essential boundary conditions, the clues from outside that any theory of the inside must satisfy. The size of the shadow confirms the predicted size of the event horizon. The energy of the jets reveals the power of the black hole's spin. The silence of gravitational waves after a merger suggests the new, larger black hole has quickly settled into a calm, simple state, just as the No-Hair Theorem predicts. Every flicker of light, every wobble of a star, and every ripple in spacetime is a piece of a puzzle, painting a vivid portrait of an object that, by its very nature, forever conceals its deepest secrets. Einstein's field equations are a silent symphony of the cosmos, written in the language of differential geometry. They tell us that matter and energy do not merely sit within space and time. They actively shape the stage itself, curving the fabric of spacetime. This curvature is what we feel as gravity, and in its most extreme form, this warping creates the event horizon. The solutions to these equations for black holes are like finding the precise architectural blueprints for a cosmic abyss. For a simple, non-rotating black hole, the Schwarzschild metric provides the map. It reveals a point of no return at a specific distance from the center, defined by the elegant formula for the Schwarzschild radius. This radius is equal to 2 times the gravitational constant times the black hole's mass, all divided by the speed of light squared. This simple calculation, born from profound theory, gives you the exact size of the invisible sphere from which nothing escapes. But our universe is rarely so still. Most black holes spin, and for these dynamic objects, the Kerr metric takes over. This mathematics is far more complex, describing a black hole that drags the very fabric of space around with it like a cosmic whirlpool. This is the frame-dragging effect, a prediction confirmed by detailed observations of orbiting matter. The equations show that a spinning black hole's event horizon is actually smaller than that of a stationary one with the same mass, its rotation fighting against the inward pull of gravity. To understand the path of any object from a photon to a doomed spacecraft, we turn to the geodesic equations. These are the mathematical rules that dictate the straightest possible paths through curved spacetime. Near the event horizon, these paths all bend inexorably inward. There are no outward-bound trajectories left, no geodesics that lead back to the universe you left behind. It is a one-way street written into the geometry of reality. As you follow these paths inward, the mathematics begins to scream a warning. The equations for time dilation become extreme. Your clock, from the perspective of a distant observer, ticks slower and slower. The factor that describes this slowing, derived directly from the metric, approaches 0 as you near the horizon. This is not an illusion, it is a direct prediction of how deeply gravity warps time. For the observer far away, your approach to the horizon stretches across an infinite future. Yet for you, the fall continues in a finite and fleeting moment. The math also points to its own breaking point. Deep within, the terms in the metric equations themselves diverge toward infinity. These are the singularities, the points where density and curvature become infinite and our current laws of physics simply give up. The great astrophysicist Subrahmanyan Chandrasekhar dedicated much of his career to solving these complex equations, often describing their mathematical beauty with a sense of awe. He saw in their stark predictions a profound truth about our universe. How can scribbles on a page so accurately predict the behavior of the most violent objects in existence? These equations are more than just descriptions, they are guides. They lead us right to the edge of our understanding, to the very precipice where classical gravity must hand the baton to a theory of quantum gravity. The infinities they reveal are not failures but signposts pointing toward a deeper layer of reality we have yet to uncover. The existence of black holes might be a prerequisite for our own. A cosmos without these gravitational pits would be profoundly different and likely sterile. This idea is framed by the Anthropic Principle, which observes that the fundamental constants of our universe appear finely tuned to allow for conscious life. Black holes are not cosmic accidents, they are integral players in this life-permitting architecture. Their influence begins on the grandest scales, At the heart of nearly every galaxy, including our own Milky Way, sits a supermassive black hole. These colossal entities act as gravitational anchors, their immense pull helping to shape the galaxy itself during its formation, but their role is far from passive. As matter falls toward the event horizon, it releases enormous energy, heating surrounding gas and driving powerful winds. This activity regulates the rate of star formation, preventing the galaxy from using up its cosmic fuel too quickly in a frantic burst of short-lived stars. Without this central engine to maintain order, galaxies might not have the stable, long-lasting environments necessary for life to emerge and evolve over billions of years. The astronomer Royal Martin Rees has long argued that our universe's habitability depends on a delicate balance of such violent and creative processes. On a smaller scale, stellar mass black holes are themselves born from cataclysm. They are the remnants of massive stars that end their lives in supernova explosions. These titanic blasts are the universe's primary forges for heavy elements. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the hearts of stars and then scattered across space by these supernovae. A black hole is the gravitational signature left behind from that creative destruction, a tombstone marking the event that seeded future planets and life. Even the violent mergers of black holes, which we now detect through gravitational waves, play a part in sculpting the cosmic landscape. These ripples in spacetime carry energy across the universe, a subtle but constant background hum from countless collisions that may influence the large-scale structure of the cosmos. Looking to an almost unimaginably distant future, black holes may once again become central to existence. As stars burn out and galaxies fade, black holes will be among the last bright objects in the cosmos. Their slow evaporation via Hawking radiation could provide the final, faint source of energy for any far future civilization. From the creation of the essential elements of life to the regulation of entire galaxies and a potential role in the cosmos's final act, black holes are woven into the story of our universe in a way that makes our own presence possible. Their terrifying darkness is not a contradiction to life, but perhaps a necessary part of its deep and enduring light. The event horizon stands as a stark symbol for the ultimate limit of human knowledge. It is a boundary in the cosmos beyond which our questions may never find answers, a permanent veil over a part of reality. This challenges our most basic assumptions about the universe and our place within it. The philosopher Thomas Kuhn described science as a series of paradigm shifts, where old ways of thinking are shattered by new, revolutionary evidence. Black holes are precisely that kind of disruptive force, breaking our classical understanding of space, time, and information. They force us to invent entirely new languages like quantum gravity, just to ask the right questions. This cosmic boundary echoes a much older philosophical idea from Immanuel Kant, who distinguished between the noumenon and the phenomenon. The noumenon is the thing as it is in itself, independent of our observation. The phenomenon is how that thing appears to us. A black hole is the ultimate expression of this division. The swirling accretion disk, the gravitational lensing, the Hawking radiation, these are all phenomena we can observe and measure. But the true nature of what lies beyond the event horizon, the black hole in itself, might be a noumenon, a reality forever inaccessible to our instruments and our senses. Physicist Carlo Rovelli often reflects on this, suggesting that black holes teach us a profound humility. They remind us that the universe is not obligated to be comprehensible to the human mind. There may be truths that are fundamentally, structurally unknowable. This raises a poignant question about our quest for understanding. Is the goal of science to uncover every secret, or is it to continually push against the edges of the unknown, expanding the sphere of our knowledge even if some mysteries remain eternally in shadow? This philosophical perspective enriches the entire scientific journey. It transforms the event horizon from a simple physical barrier into a metaphor for the human condition, forever reaching for wonders that lie just beyond our grasp. These cosmic enigmas have long escaped the confines of astrophysics to become powerful fixtures in our collective imagination. In cinema, a film like Interstellar presents the black hole gargantua not merely as a physical object, but as a narrative device for time dilation, love, and human connection, transforming hard science into a deeply emotional journey. This reflects a broader societal fascination, where black holes embody our deepest fears of the unknown and our wildest hopes for transcendence. Their cultural lineage stretches back to ancient myths of bottomless pits and cosmic serpents swallowing the sun, archetypes of primordial dread that have simply been recast in a modern scientific light. In literature, authors like Arthur C. Clarke used black holes as gateways to profound cosmic mysteries, challenging characters and readers alike to confront the limits of human understanding. The visual arts are equally captivated, with installations and paintings attempting to render the sheer awe of an infinite gravitational well, often portraying them as dark, beautiful, and hypnotic vortices. Science communicators like Neil deGrasse Tyson emphasize that this popularization is vital, translating abstract equations into relatable stories that spark curiosity in a new generation of explorers. The influence permeates even our daily entertainment. Video games cast black holes as tactical hazards or powerful weapons. Music albums use them as metaphors for existential emptiness or gravitational love. And in psychology, the term can describe a traumatic memory that pulls all other thoughts into its dark core. Economists similarly speak of financial black holes, vast sums of money vanishing without a trace. This pervasive symbolism creates a powerful feedback loop. The more black holes appear in our stories and art, the more the public wonders about their true nature, which in turn fuels support for scientific missions like the Event Horizon Telescope. They are more than just objects in space. They have become cultural icons that actively drive our desire to look up and ask what lies beyond. These cosmic questions are about to meet their match in a new generation of tools. Our view into the dark heart of a black hole is about to become sharper than ever before, thanks to ambitious missions designed to listen to and see the universe in revolutionary ways. The upcoming space-based observatory LISA, the Laser Interferometer Space Antenna, will open a completely new window onto the cosmos, while ground-based detectors like LIGO feel the high-frequency chirps of stellar mass black holes colliding. LISA will sense the low-frequency rumble of the universe. It will detect the gravitational waves from the mergers of supermassive black holes, events so colossal they shake the fabric of spacetime for millions of years. By tracking these slow, majestic dances, we will learn how these giants grew to such immense sizes and how they shaped the galaxies around them. Pioneers like Kip Thorne, whose work laid the foundation for gravitational wave astronomy, are deeply involved in designing these exquisite instruments. Their sensitivity will be so profound they could potentially detect subtle anomalies in the signal, tiny deviations from Einstein's predictions that might point toward the long-sought theory of quantum gravity. Closer to home, the next-generation Event Horizon Telescope is expanding its reach. By adding new dishes across the globe and even planning for space-based radio telescopes, this virtual instrument the size of Earth will achieve unprecedented resolution. We will move from a single, iconic image of a black hole's shadow to detailed movies, watching in real time as hot plasma orbits the event horizon and magnetic fields twist into powerful jets. This is not just about getting a better picture, it is about observing the dynamics of physics in the most extreme environment nature provides. How does energy escape from the very brink of the point of no return? These observations will tell us the sheer volume of data from these projects is staggering, far too much for any human team to sift through. This is where artificial intelligence and machine learning step in. Advanced algorithms are already being trained to find subtle patterns in the noise, to identify the unique gravitational wave signature of an intermediate mass black hole, an elusive category of object that has so far mostly evaded detection. They can also model the complex fluid dynamics of accretion disks with a speed and accuracy that was once impossible. One of the most exciting targets for these new tools is the final moment after a black hole merger. When two black holes collide and become one, the new, larger black hole does not simply sit in silence. It vibrates much like a struck bell. It rings down, emitting gravitational waves at specific frequencies that are determined solely by its final mass and spin. By carefully analyzing this ringing, this spectrum of spacetime vibrations, we can test whether the object that formed is truly the simple black hole described by the No-Hair Theorem. Any deviation from the predicted tones would be a monumental discovery, hinting at exotic structure or even a stubborn fuzzball lurking behind the event horizon. What breakthroughs await in the coming decades? The future promises to bring us closer than ever to understanding what lies beyond the event horizon, not through pure theory, but by finally listening to the whispers of spacetime itself. Creating a black hole is a feat that could redefine our future, yet it carries risks we are only beginning to fathom. The theoretical possibility of forming microscopic black holes in particle accelerators has ignited fierce debate, echoing the public fears surrounding the Large Hadron Collider. While most scientists agree the natural cosmos produces far more energetic collisions, the mere hypothetical risk forces a profound ethical question. Should we ever deliberately create an object that could, in a worst-case scenario, swallow our planet? Visionaries like Stephen Hawking cautioned that such an experiment could be the ultimate gamble, where the stakes are the entirety of human civilization. The potential benefits are staggering, offering nearly limitless energy or portals for travel, but the price of a miscalculation is absolute. This is not just an engineering challenge, it is a moral one. Who gets to make that decision for all of humanity? The power to manipulate a black hole would be the most concentrated form of control ever imagined. If one nation or corporation could harness a black hole for energy, it would create an economic and political divide unlike any in history. The technology could solve our energy crises, powering cities for millennia from a single microscopic source, but it could also become the ultimate weapon or a tool of irreversible dominance. Physicist Michio Kaku often outlines the incredible benefits for an advanced civilization, from starship engines to quantum computers, yet he too underscores the inherent perils. The ethical dilemma is starkly clear. Do we risk a catastrophic accident in pursuit of a cosmic power source? And if we succeed, how do we ensure this godlike ability does not lead to tyranny or war? The environmental implications are equally unsettling. Imagine using a captive black hole as the universe's ultimate waste disposal unit, funneling our nuclear refuse or plastic pollution beyond the event horizon. It seems a perfect solution until you consider the unknown. Hawking radiation suggests that black holes slowly evaporate, and we have no idea what happens to the information and structure of what they consumed during that final burst. Could our toxic waste be transmuted and released back into the cosmos in some unpredictable form? We would be treating a fundamental structure of spacetime as a garbage incinerator, with consequences we cannot possibly foresee. This forces a new kind of environmental ethic, one that extends beyond our planet to the cosmic ecology. We are contemplating the permanent alteration of the universe's fabric for our convenience. The need for a robust ethical framework is urgent, even for a technology that may be centuries away. It demands unprecedented global cooperation and regulation, a shared commitment to proceed with wisdom and humility rather than reckless ambition. How do we write the rules for a power we do not yet possess, but one that could ultimately define our legacy among the stars? Black holes are the architects of cosmic structure, their gravity weaving the large-scale tapestry of the universe from the very beginning. In the hot, dense moments after the Big Bang, tiny fluctuations in density could have collapsed directly into primordial black holes. These ancient relics, some perhaps no heavier than a mountain range, would have been among the first gravitational seeds in the cosmos. Their collective pull could have accelerated the formation of the very first stars and galaxies, drawing in the primordial gas that would eventually ignite into the lights that ended the cosmic dark ages. This influence extends into a profound mystery of modern astronomy, the tight correlation between a galaxy's central black hole and the properties of its galactic bulge. The mass of a supermassive black hole is often a precise fraction of the mass of the stars swirling around it. This is not a coincidence. It is evidence of a deep co-evolutionary dance. Astrophysicists like Simon White use sophisticated simulations to model this relationship, revealing how a black hole grows in lockstep with its host. The mechanism is a powerful feedback loop. As a supermassive black hole actively feeds on surrounding gas, it doesn't do so quietly. The immense energy released from the accretion process heats the galactic gas, driving colossal winds and sometimes launching jets of plasma that stretch for thousands of light years. This energetic outburst acts as a cosmic regulator, blowing away the raw material for star formation and effectively putting a brake on the galaxy's growth. The black hole, in its fierce hunger, ultimately limits its own food supply and dictates the pace at which new stars are born. How does a phenomenon confined to a tiny central volume command an entire galaxy? The answer lies in this energetic conversation between the black hole and its environment, a dialogue that shapes the galaxy's very structure and destiny. This influence ripples out further to the epoch of reionization. The intense ultraviolet radiation from quasars, the luminous cores of active galaxies powered by voracious black holes, is thought to have helped strip electrons from the neutral hydrogen that filled the early universe, rendering it transparent to light and setting the stage for the cosmos we see today. The growth of these cosmic giants is a story written in two parts: slow and steady accretion from surrounding disks of gas, and violent, decisive mergers. When two galaxies collide, their central black holes eventually sink to the new core through dynamical friction, entering a tight orbital dance. As they spiral closer, they stir the fabric of spacetime itself, emitting gravitational waves that carry away orbital energy. Their final merger is one of the most energetic events since the Big Bang, releasing more power in an instant than all the stars in the observable universe combined. These gravitational wave signals, now routinely detected by observatories like LIGO and Virgo, provide a direct record of these cosmic collisions, allowing us to map the history of black hole growth across cosmic time. This grand narrative stretches to the universe's final chapter. In a distant future, long after the last stars have flickered out, black holes will be among the only significant structures left. They will slowly, over eons that dwarf the current age of the cosmos, evaporate away through the relentless whisper of Hawking radiation. Their final pops of existence will be the last sources of light and energy in an otherwise dark and cold cosmos. From seeding the first structures to being the last sentinels of a fading universe, black holes are not merely destructive anomalies. They are fundamental, dynamic engines driving the evolution of the cosmos from birth to its ultimate end. The universe's first black holes might not have been born from dying stars. In the searing heat of the cosmos' first second, pockets of space could have collapsed under their own intense density, forging primordial black holes directly from the raw energy of the Big Bang. These hypothetical relics, studied for decades by physicists like Bernard Kerr, are a completely different class of object. They could be almost any size, from as light as a small asteroid to heavier than many suns, all depending on the specific conditions in that fleeting, violent moment of creation. This makes them perfect candidates for the universe's missing mass. Vast numbers of asteroid-mass primordial black holes could be drifting through our galaxy right now, completely invisible, forming the mysterious dark matter that holds everything together. Their subtle gravitational influence might even be the hidden force that guided the formation of the very first stars. The evidence for their existence is still indirect but tantalizing. Some of the unexpected gravitational wave signals from black hole mergers could be explained if the colliding objects were these ancient primordial bodies. Even the pattern of asteroid impacts on Earth and the Moon has been scrutinized, asking if occasional strikes were not from space rocks, but from these invisible, dense specks. The smallest of these black holes live fast and die young. One with the mass of a mountain would evaporate in a brilliant flash of gamma rays via Hawking radiation, a final burst that we might one day detect as a mysterious, short-lived blip in the sky. Larger ones are the focus of dedicated searches using gravitational microlensing, where their gravity briefly focuses the light of a background star, betraying their silent passage. What secrets do these ancient objects hold? If we find them, we are not just discovering another type of black hole. We are holding a fossil from the universe's very first moments, a direct messenger from a time before stars, before galaxies, before light itself could travel freely. They are a living bridge to the dawn of time. That spooky connection between entangled particles might be the key to unlocking the black hole's deepest secret. Two particles can be linked in such a way that measuring one instantly influences the other, no matter the vast distance separating them. Einstein famously called this quantum entanglement spooky action at a distance, and its bizarre nature could be woven into the very fabric of spacetime around a black hole. Imagine one member of an entangled pair falls across the event horizon while its partner remains safely outside. This creates a quantum bridge, a thread of instantaneous connection stretching right across the point of no return. This scenario is at the heart of a revolutionary idea known as ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind. The acronym ER stands for Einstein-Rosen bridges, those theoretical wormholes we explored earlier. EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted the strange paradox of entanglement. This proposal boldly suggests that these two seemingly different concepts are actually two sides of the same coin. When two particles are entangled, they are not just mysteriously linked, they are physically connected by a microscopic wormhole. This is not a tunnel you could travel through, it is a Planck-scale bridge in the fabric of spacetime itself. If this is true, it offers an elegant solution to the information paradox. Information from an object that falls into the black hole does not need to travel back out in a conventional way, which would be impossible. Instead, it could be teleported out using the quantum link provided by entanglement. The information is preserved without anything ever having to move faster than light across the horizon, respecting the laws of relativity. This profound interplay could also resolve the terrifying Firewall Paradox. If entangled particles are connected by these tiny bridges, the event horizon might remain a smooth, peaceful region of space after all. An astronaut crossing it would not be incinerated, because the quantum connections ensure information is preserved without the need for a violent boundary. Experts like John Preskill have championed this line of thinking, seeing it as a way to harmonize gravity and quantum mechanics. We are now testing these radical ideas not in deep space, but in laboratories here on Earth. Scientists create analog black holes using supercooled atoms or carefully structured materials, simulating an event horizon to study how quantum fields behave at such a boundary. In these experiments, they can observe pairs of entangled particles, one trapped inside the analog horizon and one escaping, mimicking the Hawking radiation process. The implications ripple far beyond theoretical physics, reaching into the burgeoning field of quantum computing. The very principle of quantum teleportation, which relies on entanglement, could one day be harnessed in technologies that manipulate information in ways that seem like magic today. Could we ever use such a link to communicate across a real event horizon? The mathematics suggests it is a one-way street for information, not a two-way conversation, but the very possibility stretches our understanding of what is feasible. How does this quantum weirdness illuminate the black hole interior? It suggests that the void beyond the point of no return is not empty or chaotic, but richly structured by a web of quantum connections. The merging of these two great puzzles, black holes and entanglement, is forging a new path toward a unified theory of reality, where spacetime itself emerges from a vast cosmic network of quantum links. There is a profound beauty in the black hole's stark simplicity. Its perfect symmetry and the minimal set of numbers needed to describe its entire being speak to an aesthetic elegance that physicists often find in nature's deepest laws. This is not merely a functional description. It is an appreciation of harmony, where a few fundamental parameters like mass and spin dictate the entire complex spacetime geometry around it. The mathematics itself possesses a kind of grace, with Einstein's field equations yielding solutions like the Kerr metric that are as mathematically beautiful as they are physically devastating. Scientists like Roger Penrose have long argued that this sense of beauty is not just a feeling, but a guiding light in theoretical discovery. It was the sheer elegance and inevitability of the mathematics that led to the prediction of black holes long before we had any observational proof, and that same aesthetic drive helped uncover the laws of black hole thermodynamics, revealing a hidden unity between gravity, heat, and quantum information. This beauty transcends the equations and becomes visible. The first image of the black hole in galaxy M87 was immediately hailed as a masterpiece. The perfect dark circle of the shadow, set against the brilliant, fiery necklace of the accretion disk, created an icon of cosmic power. The colossal jets erupting from the poles are not just streams of plasma, they are sculptures carved by immense magnetic fields, visible across millions of light years. Why do we find such destructive forces so captivatingly beautiful? Perhaps it is the contrast between the serene, dark silence of the event horizon and the violent, luminous chaos that surrounds it. This aesthetic response is where science and art converge. Visualizations and simulations created by scientists are not just tools for understanding. They are works of art that translate abstract data into a form that stirs our emotions. They allow us to feel the grandeur of the cosmos in a way that a raw equation cannot. This blend of reason and wonder deepens our connection to the universe, reminding us that the pursuit of knowledge is not a cold, clinical exercise, but a deeply human journey filled with awe. Our appreciation for this cosmic beauty reveals a fundamental truth, that our drive to explore is fueled as much by the heart's sense of wonder as it is by the mind's thirst for answers. That profound silence beyond the event horizon echoes a deep, internal quiet within the human psyche. Our minds, built to navigate a world of light and return, instinctively recoil from the concept of a permanent, inescapable void. This cosmic point of no return taps into primal fears of oblivion and the utter unknown, triggering a deep-seated anxiety that is as much psychological as it is physical. Black holes become powerful symbols for our own personal challenges, representing the overwhelming problems or depressive states that feel like they might consume us entirely. Yet, this very confrontation with the immense can also be a source of profound transformation. Psychological research, led by experts like Dasha Keltner at the University of California, Berkeley, reveals that experiences of awe, such as contemplating the vastness of a black hole, can fundamentally shift our perspective. This feeling of awe has been shown to expand our perception of time, enhance critical thinking, and foster a greater sense of connection to the world around us. It is a positive, overwhelming emotion that moves us beyond our daily concerns and self-focused narratives. In therapeutic settings, the black hole is sometimes used as a metaphor. A client might describe their depression as a gravitational pull they cannot escape, or a personal crisis as an event horizon they feel they are approaching. By giving this abstract pain a name and a cosmic analogy, it can be brought into the light of understanding, making it something that can be examined and ultimately navigated. The role of education in this process is vital. Learning the science behind the phenomenon, understanding the difference between a stellar mass and a supermassive black hole, or grasping the quantum flicker of Hawking radiation, transforms the monstrous unknown into a fascinating natural object governed by physical laws. The fear of being spaghettified becomes a lesson in tidal forces, and the mystery of the singularity becomes a frontier for quantum gravity. This shift from dread to fascination is a form of empowerment. It demonstrates that our curiosity is a powerful tool, capable of illuminating even the darkest corners of existence. How does confronting the event horizon change us? It invites us on a dual journey, one that is both scientific and deeply personal. By facing the cosmic abyss, we are not just exploring the universe, we are learning to navigate the vast and often intimidating landscapes within ourselves, turning primal fear into a catalyst for growth and wonder. Our voyage through the event horizon leaves us not with final answers, but with a deeper appreciation for the questions themselves. We have navigated the violent tides of spaghettification, confronted the enigmatic singularity where physics breaks down, and witnessed the slow quantum leak of Hawking radiation. We have grappled with the holographic principle, where a three-dimensional reality is painted on a two-dimensional surface, and wrestled with the paradox of information that seems to vanish yet must be preserved. These are not mere curiosities, they are the fundamental cracks in our understanding, revealing where our most trusted theories meet their limits. Stephen Hawking's insight rings truer than ever. The greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. Black holes are the ultimate teachers of cosmic humility, constantly reminding us that for every mystery we solve, a deeper, more profound one awaits. They push us to invent new languages like string theory and loop quantum gravity in our quest to describe the indescribable. This journey does not belong to physicists alone. It invites every one of us to look up at the dark silence between the stars and feel a sense of wonder, to ponder the fate of a fallen star, to imagine the fabric of spacetime warping into a gateway, to question the very nature of reality itself. What aspect of this cosmic enigma captures your imagination the most? Is it the sheer power of the tidal forces, the philosophical weight of the information paradox, or the mind-bending possibility of wormholes? Share your thoughts in the comments below, and if you are eager for more journeys to the edge of reality, subscribe for our next deep dive into the cosmos. Thank you for joining this incredible expedition.